Right, we had come to the stage where we were talking about transverse waves on a string, and I pointed out that the boundary condition which says that the two ends of the string which are clamped, so here is a string of length L which is clamped at this end and this end. So here is 0, here is L, that is the x axis to start with. I pointed out, I mentioned that the kind of waves you can have on this string would be standing waves which would correspond to specific wavelengths. All those wavelengths are allowed which have nodes at these 2 points, and the so called fundamental harmonic, or the longest wavelength oscillation that you can have, would correspond to the following geometry. It would correspond to the wave going up, the string going up and down in this particular fashion. So every point on the string goes up and down, executes harmonic motion, executes oscillatory motion in this fashion, going up and down, such that these 2 points remain nodes. So the actual wavelength of this wave would be twice the length of the string. In this case, lambda, and that is the fundamental node, so lambda 1 is 2L, and the frequency nu 1 is equal to, it is obviously equal to the speed u divided by lambda 1, which is equal to 1 over 2L square root of T over rho. So that is the fundamental mode, It would actually correspond to a superposition of 2 waves, one of which travels in the positive x direction and the other in the negative x direction, and we will see a little later when I talk about superposition that they would lead, these 2 travelling waves would add to each other in such a way that the result is a standing wave which goes up and down. So nothing in this, nothing moves forward or backwards, every point oscillates up and down in this fashion. Well, the next oscillation that is possible has a geometry like this. Here is a full wavelength, and then at the other end of the oscillation it looks like this. So here lambda 2 equal to 2L over 2, which is equal to L itself, and nu 2 equal to 1 over L root T over rho. And the next harmonic would correspond to something which looks like this. Not drawing this too well, but this would correspond to a wavelength which is 2/3, so lambda 3 equal to 2L over 3 and nu 3 equal to 3 over 2L root T over rho. And this series goes on forever. So you actually can excite on this waves of very, very high frequency. They would not normally get excited because we have not talked about energy considerations yet, but the frequency, the lambda n, the nth harmonic, would have a wavelength which is equal to 2L over n, and the corresponding frequency would be equal to n over 2L square root of T over rho, this fashion here. Now we would like to understand from more basic considerations what governs the waves on a string of this kind. What kind of equation governs it? Is it Newton's equation? Well, the answer turns out to be yes, it is essentially Newton's equation, but written for a continuous medium. Unlike a set of particles where you have independent particles perhaps interacting with each other and you write Newton's equation for each of them, in this case we have to pay attention to the fact that the string at every point, these points are connected to each other. The string does not break. There is a tension on the string which keeps it together, and we have to pay attention to the fact that the motion of this particular point and the motion of neighboring points must be related to each other in such a way that the string maintains its integrity. So this leads actually not to differential equations for the equation of motion, but an equation which is in 2 independent variables. For a given t, you have to say something about what happens for different x's, and for a given x you have to say what happens to this point for different values of t. So not surprisingly, the equation of motion that we get, called the wave equation, is actually a differential equation with 2 independent variables x and t in this case. and these are called partial differential equations. Although we have not really gone into the mathematics of partial differential equations, I will still mention this and derive this equation because it is fairly easy to understand how this happens. Let us take the string example itself. So, we have the x axis here in this direction, and let us suppose that momentarily the string at some point looks like this. So, consider a point x and consider a point x plus dx. I have shown this exaggeratedly, this is just an infinitesimal difference here, increment. The tension at this point acts tangentially in this fashion, and the tension at this point acts tangentially in this fashion, and what we are interested in is the transverse displacement. And let me call the transverse displacement at any point x phi of x comma t. This is the transverse displacement of the string at the point x at the instant of time t. So, we have a function here, and since it is just a displacement in the transverse direction, it is a scalar function. So, this function is a function of two independent variables of both x and t, and if the string is clamped at the ends, it will satisfy some boundary conditions, but we are not concerned with that right now. We are concerned with what sort of equation does this phi satisfy. Well, looking at this element of the string here, we are concerned with what happens in the vertical direction, in the transverse direction. So, if this angle here is theta 2 and this angle is theta 1, then we are concerned with what happens to the vertical component of the force, and we equate that to the mass times the acceleration in the transverse direction. So, this thing here, if this is tension T and this is tension T, so you have T times sine theta 2 minus T times sine theta 1. This is the force in the vertical direction here. This is equal to, well, we need to know the mass per unit length, that is rho, and then there is a dx, which is the length here of this string in between, that is the mass, multiplied by the acceleration, and the acceleration of course is equal to phi delta 2 phi over delta t2. So, at this midpoint, for instance, you ask what is the acceleration of this mass of the string, this incremental portion of the infinitesimal portion of the string. Well, if the thetas are small, if the displacement is not if the oscillations are small oscillations in a technical sense, namely these things angles are very, very small, then you can approximate these angles by writing this as approximately t times tan theta 2 minus tan theta 1. But remember that tan theta is a slope at this point. So, it is the derivative of the function phi. So, this is equal to t times delta phi over delta x, because you differentiate with respect to x keeping t constant, and that is delta phi over delta x at the point x plus dx, which is this point, minus the same thing at the point x. So, this is t times this minus delta phi minus t times, this is t at the point x plus dx. So, we are even allowing for the fact that the tension itself could change as a function of x, t of x delta phi over delta x at the point x here. And what does that give you? This is approximately, if I do a Taylor expansion, it says take this function, it is t delta phi over delta x evaluated at x plus dx, subtract from it the same function at the point x. If you do a Taylor expansion of this complicated function about the point x, the leading term cancels, and what remains is the derivative with respect to x of t, which is possibly a function of x delta phi over delta x, and that is a function of x and t on this side. This quantity here should be equal to multiplied by dx So, we always have a dx sitting everywhere times dx. That is what the Taylor expansion gives. The value of this function at that point, which is this, cancels it out, multiplied by dx times the derivative of this function with respect to x, which is what I have written here, and this must be equal to, on the right hand side, rho times dx times d2 phi over dt2 at x and t. So, it looks complicated, but it is actually fairly straightforward under this approximation, and then cancelling the dx out. If t is a constant, if t equal to constant all along the string, then bringing t out, it says delta 2 phi over delta x2, and that is a function of x and t, equal to rho divided by t, but then square root of t over rho is what we identified with the speed, but that is emerging here automatically. It is 1 over u squared d2 phi of x comma t over dt2, u equal to square root of t over rho equal to wave velocity. So, this equation in general, although we have derived it here for transverse waves on a string, this equation is called the one dimensional wave equation. It is the independent variables are t and one spatial variable, namely x, and this quantity here is needed for dimensional reasons, because this is 1 over length squared d2 over dx2, and this is 1 over t squared. So, you need a speed squared here to make the dimensions right, and it is associated with, this quantity is associated with the square of the speed of this wave here, of the wave velocity here. So, that is the exact wave equation satisfied by these transverse waves. Now, one can ask, given an equation of that kind, what is the general solution to it? And not surprisingly, the general solution is of the form, so the general solution to this wave equation, without putting in anything else like boundary conditions or initial conditions or anything else, the general solution is due to D'Alembert, and it is not surprisingly of the form phi of x comma t equal to some constant, say c1, times a general function, you can absorb that constant in this function, x minus ut plus some other general function x plus ut, and it is easy to see where this comes from. It is a second order equation, so you would expect that in a loose way you would expect there are two independent solutions, and you can see where this comes from. If I took this function and I differentiated it with respect to x, keeping t constant, partial derivative with respect to x, I would get an f prime of whatever is inside. If I differentiate twice, I would get f double prime of whatever of this combination here. So, d2 phi over dx2 would be f double prime of x minus ut, where by a prime I mean the derivative of this function with respect to its argument, whatever it be. So, for a fixed t, this does not change at all, this is just a shift in x, and it is equal to f double prime. On the other hand, if I keep x fixed and do a partial derivative with respect to t, every time I differentiate with respect to t, I get again an f prime and then a minus u out here. So, a second derivative would produce a minus u whole squared times double. So, this would say delta 2 phi over delta t twice equal to c squared or u squared f double prime of x minus ut for this portion. Similarly for this, because when I take a second derivative, whether it is minus u squared or plus u whole squared, it does not matter, it is exactly the same thing. So, this also satisfies exactly the same relation, and if I therefore divide this by 1 over u squared, I get this is equal to that, and that is what the wave equation is saying. So, D'Alembert solution is obvious, more or less obvious from the structure of this equation. So, as soon as you have an equation of this kind, they are guaranteed that the solution will be a superposition of these functions here. Now, why superposition? Because these are linear equations. This is a linear equation in phi. So, if you find two different solutions which are linearly independent, any superposition of the two is also a solution of the equation. Precisely what superposition is determined actually by the boundary conditions. So, that is for waves on a string. What about sound waves? What about sound waves in 3 dimensions, in higher dimensions? Well, not surprisingly, a very similar kind of derivation shows us that the general wave equation in 3 dimensions for any disturbance, and let me continue to call it phi, is of the form d2 phi and now a function of r and t over dt2, and then there is a speed squared 1 over u squared. This is equal to d2 phi over dx2 plus d2 phi over dy2 plus d2 phi over dz2 in 3 dimensions in Cartesian coordinates, where there is a function of x, y, z and t. You could write similarly an operator, a differential function here, a differential of some kind with respect to other coordinate systems like spherical polar coordinate systems or cylindrical polars or whatever. This function, this whatever appears here, these derivatives would be a little more complicated in that case, precisely because unlike Cartesian coordinates, the unit vectors in other coordinate systems change as a function of position. So, there are in the line element there are things, it is not just dx squared plus dy squared plus dz squared, but there are functions of r, theta and so on sitting there. We are not going to get into that now, but this is what sound waves in 3 dimensions, for example, where this would be the displacement of air, some given mass of air would satisfy an equation of this kind here. In particular, we could ask what happens if you have waves which are propagating out from a source. So, I start with the source at the origin and it is putting out waves which are isotropic and go out in all directions. Okay. What kind of wave would that be? What kind of surface would that be? Well, in that case it turns out that unlike the sines and cosines we have been talking about here, you would have waves of the form cosine or sine of not kx but k times r minus omega t, for instance, where k is the so called wave number as before 2 pi over lambda, r is the radial coordinate from the origin, but now energy considerations come into play. So, from this source as things go outwards, a certain amount of energy is pumped into this medium as the source emanates waves. Then since the surface area at a distance r goes like r squared, it is clear that if the total energy is constant, then the amplitude itself must decrease in such a way that the intensity multiplied by the total surface area gives you exactly the same amount of energy. So, that requires that this thing be proportional to 1 over r in 3 dimensions. So, that the square of this amplitude, the amplitude must decrease like 1 over r, so that the square of it goes like 1 over r squared, compensating for the increase in the surface area by a factor r squared. So, this thing is called a spherical wave, this kind of thing is called a spherical wave. You could also have other kinds of solutions, again similar to the one dimensional wave we talked about earlier, and a more general form for this would be something like cosine of k dot r minus omega t, where this vector k is called the wave vector whose magnitude 2 gives you 2 pi over lambda modulus k, and whose direction gives you the direction of propagation of the wave. We looked at it in the x direction, so this was just k dot r was just k times x, but you could have a wave which is propagating in some arbitrary direction, and then we can ask what kind of object is this, what kind of wave is this? It is not a spherical wave. Well, it would correspond to putting k dot r minus omega t equal to a constant, some given phase. And what kind of surface is it for a fixed t? You need to ask what kind of object is k dot r equal to constant. and since this stands for k1 times x plus k2 times y plus k3 times z, if k1, k2, k3 are the Cartesian components, this equal to constant, it is a plane. This is a plane, an infinite plane in some direction, the direction of this vector k here. If you of course had no third dimension here, then it is a straight line, as you can see, and it is a plane in 3 dimensions. So this is called a plane wave. Something like this is called a plane wave when we study 3-dimensional waves. One more generalization. What about light? What about light propagating in a vacuum? We know that light consists of electromagnetic waves, which means it is the electric and magnetic fields that oscillate, and there is no medium here. The speed of light is the same no matter which direction you are in. In fact, it is independent of the source, state of motion of the source or the observer according to special relativity. So what kind of equation is satisfied by the electric and magnetic fields in that case? The equation is exactly the same thing, except that this becomes a vector, the electric vector, field vector here, and similarly for the magnetic field B R and T. And this u in vacuum is replaced by the speed of light in vacuum, and that is the wave equation satisfied by the electric field in an electromagnetic wave, of which light is an instance. So visible light is one such instance. Light of any frequency is an electromagnetic radiation, and in vacuum it has got this invariant speed of propagation c here. So as you can see, the general wave equation has a large number of a very comprehensive kind of equation. It can have all possible kinds of solutions depending on the situation, much more complicated than the simple transverse waves on a string that we have been talking about here. Next, let us look at superposition of waves. So let us suppose that we have 2 waves, one of which is a cosine of kx minus omega t, a travelling wave in the x direction, a one-dimensional wave in the x direction with a velocity, a wave velocity which is omega over k, and we also have along with it the same time the medium has a disturbance which is k plus some delta k x minus omega plus delta omega t. So we have 2 waves, one of which travels in the x direction with a speed omega over k, and the other has a slightly different frequency and a different wavelength here or wave number. So what does this superposition give us? Well, we need to simply use the identity that the cosine of the sum of these 2 guys is equal to twice the cosine of the sum of the 2. So this is 2k plus delta k x minus 2 divided by 2 omega plus delta omega t divided by 2, that is the cosine of this, the sum of the 2, sorry 1 2 here, times the cosine of the difference of the 2, which is delta k x minus delta omega t divided by 2. So we could write this as k plus delta k over 2 x, get rid of this, and what does it geometrically look like? Well, you can see that these quantities are infinitesimal quantities. If you say that delta k and delta omega are very small compared to k and omega, they are infinitesimal quantities. So the variation mostly comes here due to this, and once you put that envelope in, you can bring that factor down to this portion and consider it as part of the amplitude. Then this phase thing looks like this, whereas originally you had a single cosine going up and down and another cosine going up and down. When you join the 2 together, when you superpose them, then the whole system looks like this. Schematically, and so on, and the actual disturbance looks like this. And this wavelength here is much larger than this wavelength here. This wavelength here is given by a wave number which is k plus delta k over 2. So, it is the mean between k and k plus delta k, k plus half the difference here. So, this is 2 pi over the corresponding k. So, that is k plus delta k over 2 here. On the other hand, this is 2 pi divided by that wave number which is therefore 4 pi divided by delta k. So, at a given instant of time the disturbance looks like this. In other words, there is this original oscillation whose frequency is the average, whose wavelength is the average of the wavelengths of the two that we have superposed, the two waves we have superposed, multiplied by an envelope function which has got a much slower variation. It is also a travelling sinusoidal wave, but it is much longer wavelength than the original two waves individually had here. At the same time, this is also travelling along, and what is the speed of travel here? It is the speed of this cosine here. So, this would correspond to a wave, a velocity or a speed of this envelope wave is delta omega over delta k, or this tends in the limit to d omega over dk if omega is a function of k. So, the point is I superposed two of these waves and I found that there is an envelope which is travelling at a speed which is given by d omega delta omega over delta k from this portion here. It is a much longer wavelength thing. So, this looks like this wave, original two waves have now broken up into groups. There is a group here and that group as a whole is travelling with this speed here, and this is called the group velocity. In general, what happens is if I superpose a large number of these k's, a whole set of these k's such that omega is a function of k. So, for each k there is a corresponding omega, then what I have is a wave packet, and this wave packet will travel as a group. The group velocity of this wave packet is given by d omega over dk, whereas for a given k and a given omega of k, the wave velocity equal to omega, which in general is a function of k over k, and the group velocity, I should really say speed, but this is the standard terminology, is d omega k over dk, and these two could be very different from each other as we will see. Okay. So, if you got a single wave there is no problem, but the moment you have a whole collection of waves of different frequencies superposed, then you have both a wave velocity, individual wave velocities, as well as a group velocity d omega by dk. Of course, it might turn out that omega is the same for all k's. In other words, the frequency is independent of the wavelength. The speed of the wave is exactly the same for all wavelengths. Okay, I should not say the frequency is independent of the wavelength. What I should really say is that the speed is the same for all wavelengths, which is what happens to light when it propagates in vacuum. In that case, it is clear that the frequency and the wavelength are related by nu times lambda equal to c, or if I write it in terms of k, etc., omega equal to ck. So, exactly the same thing, same relation. And once omega is a linear function of k, this will imply that d omega by dk equal to omega by k equal to c. In other words, for light propagating of different wavelengths propagating in a vacuum, even if it is a wave packet, the group velocity and the wave velocity are exactly the same. Okay. The wave velocity is the same for all wavelengths and the group velocity is the same as that wave velocity. What does that mean? It means that this group does not lose its shape, this wave packet does not lose its shape, it does not disperse. So the origin of dispersion lies here. It lies in the fact that different wavelengths have different travel at different speeds, and d omega over dk is not the same as omega over k. But in this special case of light in vacuum, it happens to be so. It also happens to be approximately so when you have sound waves propagating in air. It turns out that under normal conditions the dispersion is very minimal, is very little, and therefore all wavelengths of sound propagate at exactly the same average speed, and therefore you do not see dispersion. But of course the moment light, for instance, travels through a medium, you see this immediately, which is why a prism breaks up light into different colors, because the speed with which different wavelengths travel is different in the medium. We have considered wave motion rather briefly. We are going to do a lot more of it in the context of light and optics, when we will talk about electromagnetic waves at greater length. But one particular topic in wave motion which is of great practical significance and great importance has to do with the Doppler effect. Now this is an effect that all of you are familiar with. When you hear a siren approaching you, for instance, as it approaches you it appears as if the frequency of the siren increases, and as it departs from you it appears as if the frequency goes down. So the pitch of the siren increases and then it decreases as it passes you. This effect is quantifiable, it is a very important effect, and it is known as the Doppler effect after its discoverer. What we are going to do is the simplest case. I am not going to derive this in great detail here, I am simply going to point out what the main effect is. So we will look at a situation where you have waves in a medium. So let us suppose that the waves in the medium have frequency nu naught, say, in a stationary medium. So we look at sinusoidal waves of a given frequency nu in a medium which is stationary. Then if you have a source here, and let us say, or you have an observer here, let us say observer, and the source of waves is here, we will consider only the case where the observer or the source is moving, one is moving with respect to the other along a line joining them. So we will not look at situations where the source moves like this, for example, and the observer is here with the transverse component. We are only going to look at the simplest case where the observer and source either move towards each other or away from each other, and then ask what is going to happen if, for example, the source starts moving either towards or away from the observer. Well, we need a convention here for the velocity of the source or the observer with respect to the other person. So let us suppose that the source moves out in this fashion, and let me call that V source with respect to the medium. So the source is starting to move with respect to the medium with a velocity or speed V source, and the observer is stationary. The question is, what is the observer going to see as the frequency of the waves emitted by the source, given that the frequency, true frequency if you like, is nu naught? That is one question. The other question we could ask is, and of course V source could be in this direction, so this would correspond to, let me say, V source less than 0, and this would be V source greater than 0. So the convention is that if the source moves away in this direction, V source is positive, and if it moves this way, V source is negative. Well, you could also have a situation in which the source is stationary, so let us write that down. Here is the source, and the observer either moves towards the source with a speed V observer with respect to the medium, and this would be a positive speed. On the other hand, if he moves away in this direction, V observer less than 0 in this case. So the convention is clear. When the observer moves towards the source, V observer I take to be positive, moves away it is negative, whereas in the case of the source, moves away it is positive, moves towards it is negative. So this picture makes it quite clear as to what our conventions for the signs of these velocities are. Then we have several cases possible. We have a case in which the observer is stationary and the source moves, or the source is stationary, the observer moves, or both of them move with these given velocities here. The general formula is what I am going to write down now, and the formula is that the observer is going to observe a frequency nu, which is nu naught, multiplied by, we need information about the speed of these waves in a stationary medium, and if the stationary medium, the speed is u, this is speed of the waves, or the phase velocity of the waves in a stationary medium. Here. Then the formula is this plus V observer divided by U plus V source. That is the general formula with these sign conventions. So you can see physically what happens is if the observer starts moving towards the source, this is a positive number here, and if the source were stationary, that is 0. So what is happening is that the frequency is increasing, because as he moves towards the source, the number of crests that he observes per unit time is going to increase, it is going to look compressed. Exactly the same thing is going to happen if the source moves towards the observer while emitting radiation or waves at a given frequency. So many troughs per crests per second, and as it moves towards the observer, the number of crests observed by the observer is going to increase. So effectively the frequency increases. On the other hand, if the source moves away, this is going to look stretched out, and therefore the frequency observed by the observer is going to drop. That is what is going to happen if V source is positive, well, that is 0, for instance. So this formula includes in it both cases, when the source is stationary and the observer is moving, and vice versa, and this is the general formula. Now what is interesting in this formula is that it is derived under the assumption of Newtonian mechanics. So there is no relativistic mechanics here, there is no special relativity here at all, and you can see immediately that it is not symmetric with respect to whether the velocity source is moving or the observer is moving. On the other hand, one could ask what happens if you have special relativity, which we will talk about in the context of electricity and magnetism later on. What happens then? After all, then neither of these frames of reference, either the observers or the sources, is preferred. There should be complete symmetry between these two, and the formula then changes in the relativistic case. But this is the non-relativistic formula, which we can plug in numbers into it, and then we can find out what the actual frequency shift is, etc., etc. But let me make a mention of what the relativistic formula is, because it is interesting to see what happens. Two things happen. Here is the observer, and here is the source. Once again we consider only the simplest case where there is a motion of either of these people or both of them is in the line joining the two, the observer and the source, and let us suppose the relative velocity between the two is some number v. Then it should not matter really whether it is the source that is moving or the observer that is moving. Besides, when we talk about light, we have yet another phenomenon to take care of, which is that the speed of light in a vacuum is independent of the state of motion of the source, of the speed of the source or that of the observer. That is a fundamental postulate in relativity. The principle of relativity is different, and we will talk about it, but the physical postulate of special relativity is that the speed of light in vacuum is a fundamental velocity independent of the state of motion of the source. Therefore, that speed is c. Then the question asked is, what is this going to be? What is nu going to be? Nu equal to nu naught times, and now we have to pay attention to two things. Not only the argument about the number of crests or the number of troughs actually getting compressed or decompressed, but also the phenomenon of time dilation. So, when you have a moving frame, time flows differently than it does in a stationary frame, provided these are inertial with respect to each other. When you put these corrections into account and put the special relativistic corrections into account, this formula is not, does not hold good anymore. We have a formula that is symmetric about whether the source moves or the observer moves, and this formula is C minus V divided by C plus V, where V equal to the relative velocity of the source or of the observer with respect to the source, and all we need to know is we do not care which of the two is moving, V is greater than 0 if the source and observer, here is the observer, here is the source, are moving towards each other in this fashion, does not matter which of them moves, and V is less than 0 if when they move towards each other, if V is positive, this is going to give a compression here, so the thing decreases, so it is the other way about. V less than 0 if they are moving towards each other, and V is greater than 0 if these are moving away from each other. And when V is positive, you can see that the increase in the frequency, the decrease in the frequency comes about for two reasons. One, because this factor becomes smaller than C, the numerator becomes small and the denominator increases, meaning that there is a decrease in the frequency. So, when they are moving away from each other, there is a decrease in frequency, but if they are moving towards each other, then this is negative. So, you have an enhancement of frequency, both because the numerator is increasing and the denominator is decreasing in proportion. So, this is the relativistic formula. Which includes the correction due to time dilation. And again I emphasize it is the longitudinal Doppler effect, in the sense that the two source and observer are, the motion of either of them or both of them is along the line joining the two of them. If it were a transverse effect, namely if you have a source here and you have an observer zipping along in a line which does not pass through the source, then the formula changes, and we will take up this as to what happens then when we study optics, when we study the propagation of electromagnetic waves.